Okay, so hello. So here are some number theory problems from the Putnam exam. Actually, it's just practice problems. And we're just going to try to go through question one right now. So question one asks, first part asks that show that n to the 7 minus n is divisible by 42 for every positive integer n. Now it's a bit weird like how you would approach this, but the first thing that you can note is that n to the 7 minus n is what we're starting with. Let me just label this as a. Okay, so this is what we're starting with. What we can do is we can take n common, so we're left with n to the 6 minus 1, right? Now you might wonder, well, what's the point of doing that? Well, a neat little thing is that n to the 6 minus 1 can be rewritten as a difference of squares. So that becomes n cubed plus 1 times n cubed minus 1. Now, what's even better is that we can again rewrite this as a difference, but now it's a difference of cubes. Now, unfortunately, I don't actually remember the formula for this, but what I can do is I can look it up. So difference of cubes formula, and and the reason why I'm going it's a difference of cubes is because this is clearly n cubed and one is 1 cube. So yeah. Okay, so the formula goes that if it's a cubed minus b cubed, then it's a minus b. So a minus b, so that'd be n minus 1. And then this is going to multiply with a squared plus ab plus b squared. So n squared plus ab, so that would be plus n, and then plus b squared, which is plus 1. And this is kind of similar, except now, so I mean, there's a formula for a cube plus b cube as well. So a cube plus b cube formula. Hopefully I got the right thing. Yeah, so it's a minus b. So this becomes, wait, that's the same. So that's a cube minus b cube, sorry. Um, yeah, okay. A plus, nope, this is not the formula I'm looking for. So many formulas I don't need. Okay, yes, this version. A plus b, so n plus 1 times a square minus ab plus b square. So n square minus n and then plus 1. And so this is our overall complete expansion. Beyond this would be hard to go. Now you might say, okay, what if I don't actually know the expansion for this? Well, one thing that you do know is that for each of these, one thing that you can determine is that uh, -1, so n equals -1 is a root for this, so -1 is root here, and +1 is a root here. And then with that in mind, you know that you can find the other factor of this term by dividing this by n plus 1, and similarly you can find the other factor for this term by dividing by n minus 1. But yeah, that's how you could do it if you don't remember them like I do, but I just googled it because I'm lazy. And that gives you this whole expression. Now, it might be a bit confusing, like what does this even do for us at all in the long run? Like how is this related to our question? Well, to figure out why this was useful, we need to first realize what exactly is 42. Now, other than it being the answer to life, it is also a product of the numbers 2, 3, and 7. So that this is 6, and then 6 times 7 is 42, right? So this is a multiple of 2, 3, and 7. So what's really nice about this whole expression is that everything here is multiplying. So if I can show that whatever this is, it's going to be a multiple of 2, a multiple of 3, and a multiple of 7, then that would show that it is overall a multiple of 42. Now that's very wishful, right? But we're going to see that our wishfulness works out here. So let me just try a red pointer. So we're going to first work for 2. Well, we know that if two consecutive numbers are being multiplied together, a times a plus 1, in fact, let me write that underneath 2. So a times a plus 1. If these are two consecutive numbers, then one of these is going to just be even by like a pigeonhole principle per se, right? So either a is odd, but if a is odd, then a plus 1 is even. So the overall thing is even. Or a is even, in which case, again, the overall thing is even. So what that means is that we have two consecutive integers. The overall result is even. So we do have two consecutive integers, which means that this thing is even, and then just multiplying it with the rest of this will still give us an even number, because all of this, no matter what it is, it's going to be an integer. So it's just an even number times an integer, so that's going to give us an even number, so that's fine. And we know this is all an integer because n is an integer, so all of these expressions should be integers because there is no fractional parts and blah blah blah, blah. But that shows that, okay, so let me just keep this underlined. So that shows that 2 is met. Okay. So now let me try different numbers. Let me try uh let's try 3. Okay. So a similar trick can work, that if I have 3 consecutive numbers, so a and a plus 1 and a plus 2, I again know that one of these has to be a multiple of 3. And this is something that you can confirm for yourself. But what I'll just simply do is that I'm going to highlight this and this, because now these are 3 consecutive numbers. Because if we start at n minus 1, then the next number is n, and the next number is n plus 1. So 3 consecutive numbers are multiplying together, and then, this and this are just 2 other integers, so that doesn't really matter. But yeah, we've shown that this is a multiple of 3 as well. Now, the last point is, how do we show it's a multiple of 7? Now, there might be other ways of doing this. I'm not particularly sure. Maybe you could somehow evaluate this expression. And in fact, you could probably test it for a bunch of mod values, remainder values, and show that it works. The way I will just go about is I'll mention Fermat's little theorem. Okay, and Fermat's little theorem states that if p is a prime number, then for any integer a, the number a to the p minus a is an integer multiple of p, which is a mouthful, but essentially it's saying for any integer a, okay, a to the p minus a is a multiple of p if p is a prime number, which means that so a to the p minus p is minus a is a multiple of p, which means p divides this. And now let's start plugging things in. So let a equal n and p equal 7. So by this theorem, we know that 7 divides n to the 7 minus n. Or I could have just written a, that's arbitrary, but the point is that we can show by Fermat's little theorem that this expression has to be divisible by 7, which just means that it is also, so if it's also divisible by 7, is divisible by 3 as we showed earlier, so it's therefore divisible by all 3 of these options, meaning overall it is in fact divisible by 42. So 42 divides n to the 7 minus n, and this is shown, right? Maybe I'll have a nice little box here, even though I don't know if that is completely perfect to have. Okay, so that's great. One thing I want to now do is see if I can copy. I'm very new to this. Okay, yes, I can copy and paste. Let's go. Maybe I probably shouldn't have copied and pasted, but oh well. So then the next question is, okay, we've done part A. That's great. Good job. What about part B? And for this, I'm going to more so try to demonstrate, but hopefully through that, there's some idea of where my thinking is coming from. Okay, so for 1b, show that every prime number not equal to 2 or 5 divides infinitely many of the numbers 1, 11, 111, 1111, and so on. Now, uh, let's just figure out what this is saying. So it's saying all primes divide infinitely many terms of this other than the primes 2 and 5. Okay, so that's still a very abstract statement maybe, but you can think about this for a bit and figure out what exactly it's saying. And now let's actually try to work on this, right? So let's firstly try to understand this sequence a little bit better. So we see is that the number of ones is constantly increasing. Well, one way that we could write this is that, let's say t of 1 is 1, and then we can define the series recursively such that t of n equals 10 times t of n minus 1 plus 1. What this essentially means is that, okay, if I want to go from one term to the next, I just multiply this number by 10 and add 1. And I can confirm that because essentially what's happening is multiplying this by 10 is just like shifting it one place to the left. So that's 1, 1, 0. And then adding 1 just converts this 0 into a 1, right? And this would work no matter how long it is. So if I applied this process on this would just add a 0 and then convert that 0 into 1. If I did it again, I would add a 0 and then convert that 0 into 1, simply by the process of multiplying by 10 and then adding 1. And that way I can generate this sequence. So this is a nice recursive way of defining the sequence. Now, from that, we can do some fancy stuff. But before I do anything fancy, I want to make a small little comment. So, I don't like this statement in particular. So what I want to do is I'm trying to replace this with a statement that every prime divides infinitely many of the following of infinitely many terms of the following sequence. So that sequence is 0, 1, 11, 1, 1, 1, 1, 1, 1, 1, dot, dot, dot. And you'll see that this is identical to the original sequence. It's only that I add a 0 here. Why I did that, it'll be hopefully apparent in a minute. But we can also argue that these two statements are equivalent, because what I've done is I've just added an extra 0. So I've only added a finite amount of terms. So if this statement was already true, right? If this statement was already true for this, then adding the 0 does nothing. If the statement wasn't true for this sequence, then adding the 0 can at most add one number which is divisible, which is 0. But that's not infinite. And so these two statements are oddly equivalent, with the statements for both of these sequences are equivalent. And that is really convenient for us, because the nice little thing is that all primes, so all p in p, so all primes, it's just a convenient way to write this, where capital P refers to the set of primes. So all primes divide 0, right? For all primes, all of them divide 0. So that's great. So I already know all of the terms in my sequence divide at least one term. So all the primes divide at least one term for my sequence. Now, another fancy thing that I'm going to try to show is this. So I made the claim that if P divides some term I, Also, just to clarify, in here I'll just call t of 0 equals 0, and then I'll use this same recursive definition, okay? Because I know 0 times 10 plus 1 is just 1, right? So this still gives me the same t1, so there's no problem there, right? And now what I can argue is that, okay, let p divide some term in my sequence, then p divides some other term in my sequence, term j to be exact, where j is greater than I. Okay, so how could I go about showing this? And firstly, this statement is true for all of the primes, because I already showed that since 0 is in my sequence, so all the primes at least divide one such number. So that's a given, okay? Which means I can just focus all my attention onto this statement. Now, this is the part which gets a little bit tricky for me to explain, but hopefully I do a decent enough job because I'm writing this out for the first time. So the claim I'm trying to make is that, okay, let's say we're working with P, which is a prime. For all remainders with respect, so for all remainders x with respect to P. So keep in mind, a remainder with respect to P just means that the remainder is from 0 to P minus 1. And let's say like my prime that I'm dealing with is 3. Well, 5 has the same remainder as 2, okay? So I'm just showing this property for a remainder of 2. Same with 7. 7 also has the same remainder as 2. So I'm just showing this remainder property for each remainder, okay? And the nice other thing is that if the property holds for the remainder, the thing I'm trying to show just falls through anyways. Hopefully, if need be, I'll try to be explicit about why. For all remainders x with respect to P, 10x plus 1, sorry, the remainder of 10x plus 1 is unique, which basically means that if I had a remainder of 2, and if I had a remainder of like 6, then if I do 10x plus 1 and I take, or sorry, 10 times 2 plus 1, I take the remainder of that, versus if I take the remainder of 10 times 6 plus 1, both of these will give me different answers. In a sense, this is injective, okay, where if my input is different, my output is going to be different. And this is a very neat property, but before we start to use it, we're going to prove it. So very simple way to prove is that we can prove this by contradiction. So by contradiction, just write contra, which is actually very misleading. So I'll just write contradiction completely. So things such as contrapositives. So that by contradiction, I assume that two remainders A and B, remainders A and B have same remainder of 10a plus 1 and 10b plus 1, where a is not equals to b, right? Which is basically saying that two different remainders exist such that this applying the function, which is 10a plus 1, 10x plus 1, gives the same remainder for both. Okay, and keep in mind that since a and b are remainders, so a and b both lie between 0 inclusive and less than p, or if I want, I can say p minus 1 inclusive. Okay, so that what that means is that 10a plus 1 has the same remainder, which we can write as is congruent to. So 10a plus 1 is congruent to 10b plus 1 mod p. So if 10a plus 1 and 10b plus 1 have the same remainder, this congruent just means that they have the same remainder. Then that means that 10a and 10b have the same remainder. Okay, but if these two numbers have the same remainder, then if I take the difference of them, what's supposed to happen is the remainders cancel out, and I'm left with a remainder of 0, which in other terms means that, so let me just rewrite this one more step. So 10 times a minus b is congruent to 0 mod p. Okay, but this just means that p divides 10 times a minus b. Okay, so if it has a remainder of 0, that means p divides this. But if p divides 10 times a minus b, and I also know that p is a prime, and p is not equals to 2, and it's not equals to 5, because again, question said that we're doing this for all primes other than 2 or 5, not equal to 2 or 5, right? So since p is not 2 and it's not 5, so it definitely doesn't divide 10, which means that p divides a minus b. But there's only two possibilities for that. So one is that a minus b so equals to 0, or the other is that a minus b is some natural number k times p. But we know that a is less than p and b is less than p, so a minus b is definitely less than p. And you can also show that's bounded below by negative p, negative p. So then this statement is impossible, because then k would not, like, there's no whole number k that you can multiply with p to get a minus b, because the point is that these two just fall in this range. So the only possibility is that a minus b equals 0. That's the only multiple of p that falls within the range of values that a minus b can take. But if a minus b equals 0, then that means a equals to b, which is a contradiction with our original claim, which means, very, very, very fortunately, it means that our claim is validated, right? And to reiterate, our claim is basically saying that if my remainder is unique, then 10 times that remainder plus 1 is going to be unique, right? What does this do? Well, the nice thing is I know all of my primes divide 0. All of my primes divide 0. Okay. If they divide 0, then 0, when I apply the function, which I'll just call it f at this point, so let f of x just be 10x plus 1. So all of my primes divide 0, so they divide this. Now, when I apply f of x on this number that they were, if I apply f of x on 0, I'm going to get 10x plus 1, which is 1. Okay, so that's fine, that's fixed. But if I apply this process again on 1, this will point to something else. So this 1 will transform into some other number, let's say a. One other short little comment I'd like to add here is that my function f of x equals 10x plus 1 is not actually just doing 10x plus 1, it's also writing that as a remainder with respect to a prime. So that's why when I do f of 1, I'm saying it gets transformed into a number a instead of saying it gets transformed into 11. Because depending on what my prime is, it might not be 11. For example, if I was working with a prime like 7, so f of 1 would be 11, but then I take the remainder with respect to 7, which would convert that into 4. So this mapping that I'm doing is from remainder to another remainder. And these nodes that I'm making are remainders. They're not just normal numbers, which was something I forgot to clear when I was saying this out. And a nice little property is that since this is unique, I know that there's no other term which points to A. Okay? Which also means that, let's say that if I apply f on a, then that becomes B. If I apply F on B, that becomes C. If I apply C on D, that becomes, F on C, then that becomes D. I know very, very fortunately that D, or any of my numbers for that matter, so let me just say dot dot dot. So what I'm going to claim here is that uh, even if I go to a number k, and I'm assuming at this point that all of these numbers, firstly, I know all of these numbers are unique. Uh, so 1 is not A, it's not B, it's not C, it's not D. And my claim is that eventually it will loop back to 0. The reason I know this will loop back to 0 is because, firstly, as I mentioned, all of these have to be unique, right? Because of the property I showed above. So one remainder, if it points to something, then no other remainder points to that, which indirectly also means that I can have no cycle. I can have no premature cycle. It cannot happen that two elements point to the same element or get transformed into the same element by F because of the property I mentioned earlier, which means that if I were to just continue drawing out this sort of graph type thing I have, there will be no premature loops like this. The only loop that will exist is we know that there was nothing initially. We didn't know what was pointing to 0, but we knew 0 was in our chain. So eventually what's going to happen is something is going to point to 0. And the reason we know that is going to happen is, firstly, I can repeat the operation an infinite number of times. That's just arbitrary. But I also know that there can be at most p nodes, right? I can't just actually just continue this to C and then to D and then to E and then so on forever, because there's only p possible remainders. Okay, so that means there's only p nodes, but I know there can't be any premature cycle. So the only option left is that this eventually has to cycle back to 0, which means that if I start with 0, I apply the operation. If I apply it enough times, it will eventually go back to 0. And then the cycle will repeat. And then the cycle will repeat. And then the cycle will repeat. What that means is that let's say this whole path is going to have a finite length, let's say x. So that means that term 0 is divisible by the prime p. But this also means that term x, hopefully either x or x minus 1 or x plus 1, but yeah, let's just say x. That means that prime p will also divide the term tx. But when it's at tx, it's essentially back here. And if it's back here, the cycle is the same. So that means p will divide t to the 2x, then it will divide t3x, then t4x, then t5x. And so this way, my prime p will divide infinitely many numbers in the sequence of operations from 0 with f of x, which is 10x plus 1, which might be very, very roundabout, and I apologize for that, but let me just try to succinctly summarize the whole claims. So firstly, the first claim that I'm making is that the sequence can be rewritten as term 1 equals 1 and term n equals to 10 times tn minus 1 plus 1. But more specifically, it can also be rewritten as this sequence, which starts with a 0. And if this statement is true for this, it's true for this, and vice versa, because I just added a single term. So if it wasn't true here, it's not going to be true here. If it was true here, sorry, if it wasn't true here, then adding a finite number of terms will not make it true here. If it was already true here, then since this series already contains all of the same numbers, then it will also be true here. Okay, so I know that proving it for this series is good enough. I already know that all primes divide at least one number from this series, and then I go on to show that if a number has a remainder with respect to a prime, if a number has a remainder with respect to a prime, then applying this function of multiplying that remainder by 10 and adding 1 will give me uh, a new remainder, which means that if I were to draw this set where it's 0, 1, 2, dot, 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 p minus 1, so these are all the possible remainders, and then on the right hand side again we have all the possible outputs which are also just remainders. I say that applying f of x maps these in a weird way, not in a weird way, it's actually a very awesome way, that no two remainders transform into the same remainder, which gives me the nice property that if I were to start from 0 and apply the function over and over and over again, uh, then I will always, since no two remainders can transform into the same remainder, that means I can't have any weird cycle like this where there's something going in, and in fact, oh, sorry, there can't be any cycle where there's two things going in to a node. Okay, and if there can't be any cycle like that, then the only cycle that can exist is that if there's one thing going into a node. Okay, but that node has to also come in this path starting from 0. And I don't know the best way to describe it, but simply speaking, some node here cannot just link back to a previous node, because any previous node already has another node pointing to it. The only node which doesn't have that happening is the 0 node, which means that if there's going to be a cycle, it's going to cycle back to the node 0. And by cycling back to the node 0, that is the same as saying the remainder is 0, because again, this was a mapping of remainders. So if the remainder is then 0, then that means that I have a cycle which is going to be finite, and by passing through that finite cycle of operations, I get back a number which is divisible. And since it was generated uh, the way it was, this number will be unique from the number that I previously had, which means that t0 is not equals to tx, which is not equals to t2x, which is not equals to t3x. And since the cycle is finite and I have infinitely many numbers, then that means I can apply the cycle infinitely many times, and therefore I can have infinitely many numbers of this form that are divisible by all primes, which was quite a tangent, but it was fun for me. And I hope that I, at the very least, learned a little bit about how to express mathematical ideas a little better, and hopefully maybe you understood something.